Hello everyone. This week we will cover Module 3 of Chem 1. We will discuss atomic orbitals and electron configuration. According to Erwin Schrödinger, electrons do not travel in a set path around the nucleus of an atom. Instead, they move in clouds of probability. These clouds are called orbitals. The quantum model of the atom describes orbitals as clouds of probability where electrons are most likely to be found. Atomic orbitals can be imagined as volumes of space in which there is a high probability of finding an electron. Each orbital can hold a maximum of 2 electrons. Electrons within an atom have quantized energies. That means each electron has a specific energy level. The lowest energy level is the one closest to the nucleus. At this level, electrons are said to be at ground state. The farther away the electron is from the nucleus, the higher is its energy level. This happens when an atom has many electrons that occupy increasingly higher energy levels. The principal quantum number is used to identify the main energy levels in which electrons are located. The lowest energy level contains only one orbital. This orbital accommodates only 2 electrons. Thus, hydrogen and helium, which have 1 and 2 electrons respectively, would need only one such orbital. The more electrons an atom has, as in the case of carbon, the more orbitals are needed to house these electrons. Electrons occupy orbitals, and orbitals combine to form subshells. Subshells are found at each energy level. There are 4 distinctly shaped orbitals that occupy the energy levels in an atom. Orbitals are designated by the letters S, P, D, and F. The s orbital is spherically shaped. The p orbital is shaped like 2 balloons tied together at their ends. There are 3 types of p orbitals: px, py, and pz. These p orbitals point in 3 different directions. The d orbitals look like 2 p orbitals joined at the middle. There are 5 types of d orbitals, each pointing at different directions. The f orbitals have more complicated shapes and directions. There are 7 types of f orbitals. Orbitals are housed in subshells. Subshells contain 1 or more different orbitals. Subshells have different energy levels. The lowest subshell has only 1 orbital, s. The first energy level contains a subshell that has only 1 s orbital. The second energy level has a subshell that contains 2 orbitals, s and p. The third energy level has a subshell that contains 3 types of orbitals, and so on and so forth up to the 7th energy level for atoms with large atomic numbers. Regardless of the orbital, each type of the s, p, d, and f orbital can hold 2 electrons. There is only one type of s orbital, so it can hold only 2 electrons. There are 3 types of p orbitals, so they can hold a total of 6 electrons. There are 5 types of d orbitals that can hold a total of 10 electrons. The 7 types of f orbitals can hold up to 14 electrons. Except for the first energy level, where only one s orbital resides, several of these orbitals can occupy different energy levels at the same time. There is a set pattern in the way electrons occupy each orbital, subshell, and energy level. This pattern is referred to as the electron configuration of an atom. All of the elements in the periodic table have a set pattern of electron configuration. Electron configuration is defined as the distribution of electrons of an atom or molecule in atomic or molecular orbitals. Knowing the EC of an atom is useful in describing the chemical bonds that can form between atoms. The electron configuration is the standard notation used to describe the electronic structure of an atom. We write the electron configuration as Ns superscript 2. The N refers to the energy level, the S is the orbital, and the 2 is the number of electrons occupying the orbital. Note that this notation is read as 2s2, not 2s squared. As mentioned earlier, different types of orbitals occupy different energy levels, starting with the s orbital at the lowest energy level. As energy levels increase, more orbitals are possible. The electron configuration is written in the same manner, in increasing energy levels from s to p to d to f. At the first energy level, the electron configuration can be written as 1s2. At the second energy level, the electron configuration is written as 2s2, 2p6. At the third energy level, the electron configuration is written as 3s2, 3p6, 3d10. There are three rules that are important for us to know when writing the electron configuration. These are the Aufbau Principle, the Pauli exclusion principle, and Hund's rule. Let's start by discussing the Aufbau Principle. The word Aufbau is a German word meaning building up. So this principle states that electrons occupy orbitals in order of increasing energy level. Following this rule, the order of filling up of orbitals starts with energy level 1 up to energy level 7. Each level contains a sequence of the orbitals s, p, d, and f. The Madelung Rule provides a visual guide of the order in which energy levels and subshells are occupied by electrons. This order follows the n plus L rule, where n is the principal quantum number or energy level and L is the azimuthal quantum number. The values of 0, 1, 2, and 3 correspond to the orbitals s, p, d, and f respectively. The Madelung Rule has certain limitations in that it applies only to atoms in the neutral state. That is, it cannot correctly represent the electron configuration of ions. There are also some transition metals and lanthanides and actinides that do not follow the order as presented by the Madelung Rule. Let's do a simple application of the Aufbau principle with the elements hydrogen, carbon, neon, and sulfur. Remember that the maximum number of electrons the s orbital can have is 2, the p orbital can have 6, the d orbital 10, and the f orbital 14. So we simply distribute the number of electrons in each atom into these orbitals at each energy level, taking into consideration the sequence and maximum number of electrons each orbital can hold. So hydrogen has an atomic number of 1. Its electron configuration is 1s1. The 1 here represents the atomic number or number of electrons. Carbon has an atomic number of 6, so its electron configuration is written as 1s2, 2s2, 2p2. Neon's electron configuration is written as 1s2, 2s2, 2p6. Sulfur has an atomic number of 16. We can write its electron configuration as 1s2, 2s2, 2p6, 3s2, 3p4. Note that among these four elements, only neon has completely filled orbitals. Neon is a noble gas, and as we learned in Module 2, the outermost shell of noble gases are completely filled. which makes them unreactive in terms of sharing electrons with other atoms. If we write the electron configuration for elements with larger atomic numbers, we will realize just how tedious it can get to write out everything from 1s2. There is a way to shorten long electron configurations by using the electron configuration of noble gases. This method is called the noble gas notation. When writing the noble gas notation, we use the electron configuration of the noble gas that comes before the element that we want to notate. Let's use chlorine as an example. Chlorine has an atomic number of 17. Its electron configuration is written as 1s2, 2s2, 2p6, 3s2, 3p5. The noble gas that precedes chlorine is neon. We did the electron configuration for neon earlier and we came up with 1s2, 2s2, 2p6. So the noble gas notation of chlorine can be written as neon 3s2, 3p5. Let's use potassium as another example. Potassium's electron configuration is written as 1s2, 2s2, 2p6, 3s2, 3p6, and 4s1. The noble gas that precedes potassium is argon. The electron configuration of argon is this series of completely filled orbitals in potassium. So, the noble gas notation for potassium can be written as argon 4s1. Another way to show how electrons fill each orbital is by using the orbital diagram or electrons in boxes diagram. In this diagram, the arrows represent electrons and boxes represent orbitals. This diagram best explains the two other rules that govern electron configuration, Hund's rule and the Pauli exclusion principle. Hund's rule states that when electrons occupy the generate orbitals, they must first occupy the empty orbitals before double occupying them. The Pauli exclusion principle states that the most stable configuration results when the spins of electrons are in opposite directions. Let's use fluorine as our example. Fluorine has an atomic number of 9. Its electron configuration is written as 1s2, 2s2, 2p5. We can represent these orbitals with their electrons using boxes and arrows as, bearing in mind that there are 3 types of p orbitals. The diagram on the left represents the correct filling of electrons for the nitrogen atom. The diagram on the right is an incorrect filling of electrons for the nitrogen atom. According to Hund's rule, empty orbitals in the same energy level must be occupied singly first before being doubly occupied. Let's draw the electron configuration of each element using the orbital diagram. Hydrogen only has 1 electron, so we draw 1 arrow in the box. Carbon has 6 electrons. To distribute these 6 electrons, we start by completely filling the lower energy orbitals first before filling the higher energy orbitals. So, we put 2 electrons in the 1s box, 2 electrons in the 2s box. This leaves us with 2 more electrons to distribute. According to Hund's rule, we fill each orbital singly first before double filling them. Let's go to neon. Neon has 10 electrons, so we fill in the lower energy orbitals first and then fill in the higher energy orbitals. So, neon being a noble gas has completely filled orbitals. Now let's go to sulfur. Sulfur has 16 electrons. So we fill in the lower energy orbitals first. 1s, 2s, 2px, 2py, 2pz, 3s2. This leaves us with 4 more electrons to distribute. According to Hund's rule, we fill each orbital singly first before double filling them. So this is the orbital diagram for sulfur. As with all rules, there are exceptions to the orbital filling sequence in writing electron configuration. These exceptions hold true for chromium and copper. If we were to follow the normal order of orbital filling, the ground state electron configuration for chromium would be Ar 4s2 3d4. The ground state electron for copper would be Ar 4s2 3d9. However, based on experimentation, a more stable arrangement is observed with the half-filled and filled subshells for these two elements. Thus, the observed and accepted configuration for chromium is Ar 4s1 3d5 and for copper is Ar 4s1 3d10. Recall our discussion on valence electrons in Module 2. We learned that valence electrons are found in the outermost shell of an atom and they determine an element's chemical and physical properties. The electron configuration can help us visualize where these valence electrons are. They belong to the incompletely filled orbitals in the outermost shell. We can designate the innermost completely filled energy levels of an atom as the core electrons, and the incompletely filled orbitals as the valence electrons. Our example below is the electron configuration of silicon. In Module 2, we learned that elements in group 14, to which silicon belongs, have 4 valence electrons. As orbitals are completely filled, core electrons become part of the inner electron configuration. The valence electrons are found in the incompletely filled orbitals. Valence electrons are responsible for many of the chemical and physical properties that are unique to each element in the periodic table. Valence electrons have the following properties. They occupy the highest energy shell. They are the electrons usually involved when bonding occurs. They determine how an element reacts. And the periodic table relates electron configuration to chemical properties. There is an easier way to know in which orbital the valence electrons of a certain element resides without having to write out its full electron configuration. The periodic table organizes elements into S, P, D, F blocks. Elements in group 1 and group 2 belong to the S block. This means their electron configuration ends with an s orbital. Group 1 elements end with an ns1 electron configuration and group 2 elements end with an ns2 electron configuration. In the p block, all electron configurations end with a p orbital. So, group 13 ends with an np1 electron configuration, group 14 ends with an np2, and so on up to group 18, which ends with an np6. The D block elements behave in the same manner. The 10 groups from 3 to 12 end with a d orbital. Group 3 ends with an nd1 electron configuration, and group 12 ends with an nd10. The period tells us at which energy level, or n, the valence electrons are. Remember that there are 7 periods in the periodic table. Each row corresponds to a period. For the S and P block, period 2 elements end with an n equals 2 shell. Period 3 ends with a N3 shell, and so on down to period 7, which ends with a N equals 7. The D block begins in period 4, but we know that in the electron configuration, the lowest energy level for d orbitals is n equals 3. Thus, the first row of the d block ends with a 3d shell. By combining the group and period information together, we can easily determine the valence electron configuration of each element. For example, calcium is in group 2 and period 4. The valence electron configuration of calcium is 4s2. What is the valence electron configuration of sulfur? Sulfur is in group 16, which ends with an Np4. It is also in period 3, so its N is 3. This gives us a 3p4 orbital. Backfilling the other orbitals in the same energy level gives us 3s2, 3p4. The noble gas preceding sulfur is neon. Therefore, we can write sulfur's noble gas electron configuration as S equals neon 3s2, 3p4. We have so far learned how to write electron configurations for neutral or ground state atoms, but we know that atoms with incompletely filled valence shells tend to follow the octet rule to achieve stability. This process leads to the formation of ions. When ions form, the electron configuration of the element changes, and the change differs between anions and cations. The process of writing the electron configuration for ions is essentially the same for neutral atoms. We follow the Aufbau Principle, Pauli exclusion principle, and Hund's rule. We know that anions gain electrons, so that means we would need to add electrons to the ground state electron configuration. When fluorine gains an electron to form the fluoride ion, its electron configuration changes from 1s2, 2s2, 2p5 to 1s2, 2s2, 2p6. Cations lose electrons, so we do the opposite and subtract electrons. When lithium loses an electron to form the lithium ion, its electron configuration changes from 1s2 to s1 to 1s2. Remember that only valence electrons are lost or gained. Let's use sulfur and potassium as examples. Neutral sulfur has an atomic number of 16. The sulfide ion gained 2 electrons. So we add 2 electrons to sulfur's atomic number, which gives us 18. The electron configuration for the sulfide ion can then be written as 1s2, 2s2, 2p6, 3s2, 3p6. Now let's go to the potassium ion. Potassium has an atomic number of 19. The potassium ion lost 1 electron, so we subtract 1 electron from its number of electrons. This gives us 18. The electron configuration for the potassium ion is 1s2, 2s2, 2p6, 3s2, 3p6. Note that the sulfide ion and the potassium ion now have the same electron configuration. When this happens, we can say that these two ions are isoelectronic with each other. The number of electrons of these two ions are also the same as that of argon, which has an atomic number of 18. So all of these three elements are isoelectronic with each other. And that ends our lecture on atomic orbitals and electron configuration. The deadline for submission of Module 3 activity worksheet will be posted in Google Classroom. Instructions on how to submit the requirements are written in the module. Thank you for listening.